In this video, we'll go over the idea of independence. Independence intuitively says that knowing one event doesn't tell me anything about the other event. But the formal definition is that the probability of A intersection B is equal to the product of the two probabilities. So the probability of A times the probability of B. So let's take, for example, the space of flips of two coins. So we have tails, 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 heads, heads, tails, and heads, heads. The probability of any one of these events, any one of these outcomes, is a quarter. So what if we say, are the flips of two coins independent? Well, the probability of tails and tails is this event. So we could think of this as tails of the first coin and tails of the second coin. Then on this side, well, the probability of getting tails on the first coin, that's going to be a half. And the probability of getting tails on the second coin is also going to be a half. So if we multiply them together, we get 1/4 as we would expect. Okay, that's a nice first check of that independence satisfies what our intuitions might say. Now, you might have thought, well, why can't I just say that the definition of independence is P of A given B equals P of A? This does work, assuming that the probability of B is not equal to 0. To see this, if we write that the probability of A given B equals the probability of A and B divided by P of B, well, if they're independent, then I can factor this probability on top as P of A, P of B, divided by P of B, and they both cancel. So you end up with P of A. So notice that this step would be a little tenuous if the probability of B were 0, but generally we're not going to have to worry too much about that in this course. So now, suppose I flip two coins again and let A be the event not tails, tails. And then let B be the event that I got heads, heads. Are these two events independent? Well, A intersection B is equal to just heads, heads. So if we draw our sample space, we have 4 possibilities. Say heads, heads is over here. Tails, tails is over here. That's crossed out. And then we just have tails, heads, heads, tails. So we know we're in here. We take the intersection. We end up over here. So the probability of the intersection is 1/4. Now, what is the probability of A? The probability of A is 3/4. So the probability of A is 3/4. And the probability of B is equal to 1/4. So the probability of A times the probability of B is equal to 3/16. So it's slightly less than what the probability of the intersection is. So what this is kind of telling us is that if they were independent, then we would expect the probability to be less than if they were independent, we would expect the probability to be less than this. So knowing A or B, that just bumps up our probability of the other event. Right? Well, if we knew B, we would know for sure this is true. And if we knew this, then it does increase our probability of knowing that it's heads, heads. So let's think of another slightly more complex example. Suppose now I roll 2 dice. So what is my omega for 2 dice? Well, it's 1, 1, 1, 2, and so on. And then maybe we're at 6, 5, and then 6, 6. So we have these tuples of die rolls. So now let A be the event that the dice sum to 7. So dice sum to 7. And let B be the event that B be the event that I roll a 2 on the first dice. So first, actually, let's say first, no, 1. First is 1. It's not going to work otherwise. So if the first die is 1 and the dice sum to 7, then the only possible event is 1, 6 in the intersection. So this is equal to A intersection B. And so the probability of A intersection B, well, this is one event out of 36 possible events. That's 1 over 36. Now, the probability of A, we know there's 6 possible ways for it to sum to 7, so the probability of A is 1 over 6. The probability of B, there are 6 possible ways the first die can be 1, so that's also 1 over 6. So what really happened here is they're independent, and what happened here is that if the first die is 1, if I tell you that the first die is 1, then I don't know whether or not the dice sum to 7, but I know that the second die has an equal chance of being any one of those numbers because the 2 dice rolls are independent. And so that doesn't affect the probability of what the second die comes out as. Now, so they each have a 1/6 chance, so that's fine. But why doesn't knowing that the dice sum to 7 tell you anything about the probability that the first die is 1? So why is this equal to just P of B? Well, if we look at the event where the dice sum to 7, there are 6 possible events. There's A equals, so we have 1, 6, 2, 5, and so on, all the way up to 6, 1. So there's 6 possible events. So the number of outcomes where the first die can be, 1, given that the dice sum to 7, it's still 1/6. So it's kind of it's a little bit non-intuitive because, especially what if I say, now I change A to B, A is the dice, so dice sum to 8. Well, now what we have is A intersection B is the empty set because it's impossible for the dice to sum to 8 if the first roll is a 1. So there's no intersection there. The probability is 0, and clearly I would be multiplying two non-zero probabilities otherwise. So it's a little bit counterintuitive here, and the reason that it works is because when I look at the set of outcomes where the dice sum to 7, there's exactly 6 of those, and one of them has what we want. So knowing that the dice sum to 7, it's still possible for the first die to take on any of the 6 possible values that it could have, and it doesn't change their likelihood. And you can try this example with other numbers too, and other first die values. And you'll get similar answers. It only works for 7 because only with 7 can the first die take on any value.